Okay, in the last video, we found the slope of this function at a not so specific point of tangency, where instead of identifying an x value like 1 or 2 or 3 or 0, we just said, you know what, we're going to choose an x value of a, and then that creates an output of f of a, which is the y value of our point of tangency, and that was a little bit more abstract way of dealing with our tangent slope, but the benefit was we had an expression for our tangent slope that allowed us to find the tangent slope anywhere on this quadratic function. So just to quickly recap that process, if we have a point of tangency that's not so specific, it still is our x1 and our y1 point of tangency, or our first ordered pair, and that would mean our second nearby ordered pair. To set up our secant slope is a plus h and f of a plus h. And remember, that is just simply function notation is saying input a plus h into your function to get your output. And then we can use our subscripts, so it's a little bit more familiar, and we can set up our slope formula with the subscript there of secant to remind us that we're just dealing with our traditional slope involving 2 points, and we have our rise over run formula, which now shows up with function notation. And now with an a in it instead of a specific number. It's the only difference, but remember, a is representing a number, usually just after the fact though, and not before we go ahead and deal with our secant and tangent slope. So that's our difference quotient, remember, that f of a plus h minus f of a divided by h. And then to change from a secant slope into a tangent slope, of course, h has to go to 0. The points move infinitely close together, and there we have the slope of our curve at any x value that we want, as long as the function is defined, which again is not an issue for our quadratic. Well, the final level of abstraction in this tangent slope journey that we're on is, instead of switching x with the letter a, let's just leave it as x. It's still our input. And our output, of course, is going to be f of x, which is the y value of our function, however it is defined. And that is still going to be our point of tangency. So instead of switching letters, we're going to keep our original independent variable, x. And our nearby point is not going to be a plus h anymore. It's going to be the initial x value of the point of tangency, x with an h added onto it. So the nearby x value is x plus h. Providing an output of f of x plus h. And guess what? That's still our x1 and y1 first order pair, and our x2 subscript 2, y subscript 2 second order pair. So we can still set up a secant slope. Now it's in terms of x and not in terms of a, which is probably a little more natural fit. And this is going to provide us with an expression for our secant slope when we identify an actual function with a specific function. This is going to give us an expression in terms of x. It might be a little more natural to recognize that all we need to do is input an x value to get, in this case, a secant slope. But of course, if we apply the limit to this difference quotient as h goes to 0, we have an expression for our tangent slope. So all we got to do is, after we take our limit and tinker with some algebra there to avoid indeterminate form, we can input an x value into our tangent slope expression. And this is the final level of abstraction in all of this tangent slope business. And this is called the derivative. And the derivative is defined as f prime of x equals the limit as h approaches 0 of our familiar difference quotients. In this case, it's in terms of x, though. F of x plus h minus f of x all over h. Of course, that is the slope of our secant line embedded inside that limit as h approaches 0. So get used to reading the prime notation. F prime of x is asking you to go through the secant slope and then tangent slope via the magic of the limit to produce not a specific tangent slope, but an expression that can give you the tangent slope anywhere. And the reason we call this the derivative is because our f prime of x function, our new tangent slope function, has been derived from our original function through the magic of our secant slope expression and the limit as h approaches 0. And when we're working with this limit as h approaches 0 of this expression, of course, stuck with limits for another little while. So when you're finding f prime of x via limits, it's called using first principles. And differentiation will be a new word that we see for the next little while as well. And differentiation is the process of finding the derivative of a function. And that process, of course, is converting your secant slope expression into a tangent slope via the magic of limits. So when you're differentiating a function, you are looking for its derivative. And last, in terms of notation, we won't use this in this video, but it's worth, I think, mentioning now. There's another derivative notation, and it's called Leibniz Notation, named after German philosopher and mathematician. So when you see dy over dx, you're being asked to find the derivative of y with respect to x. And what that respect to x business means is just that you're dealing with y that is a function of x. And where that dy over dx came from, Leibniz tried to make the connection between your good old slope formula, which is change in y over change in x. So Leibniz wanted to kind of copy that notation, and instead of using a delta notation anymore, he used a lowercase d to say, you know what, this is our tangent slope dy over dx, which is the limit of the secant slope, your ordinary two-point slope, as the difference between those 2 points, or the distance between those 2 points, goes to 0. And I better really just say the distance between those x values, delta x, goes to 0. And yes, the run goes to 0. So Leibniz notation is meant to basically copy your traditional slope formula, but with the important distinction that it doesn't represent your secant slope, it represents the slope of your curve, your tangent slope. So you could see your first principles derivative written this way as well, f prime of x, or Leibniz notation dy over dx. Okay, so here we are. We're being asked to differentiate the function f of x equals x squared minus x minus 6 using first principles, and that means we have to use limits, which are really our only option at this point. But in the next few videos, keep the faith. We're going to actually eventually abandon limits and look for shortcuts to this whole process. So differentiate the function. Now remember what that means. We're going to find the derivative, which is an expression in terms of x that finds our tangent slope anywhere. So let's go through the multi-step process. We'll write down our first order pair, which is just going to be x and f of x. So whatever my input happens to be. I don't have to choose it up front. I can choose it later. I know I input x and I output f of x. So that's my x subscript 1 and my y subscript 1, my point of tangency. And then another nearby point, it's going to be x plus h. And then input f of x plus h. And this is going to be the nearby point for our secant slope. So right now we still have, and I better label that properly, we still have two order pairs. So this, of course, is x subscript 2 and y subscript 2. So if we set up our secant slope, the slope of our secant line, of course, we're going to create our difference quotient here. So no limits yet. It'll be f of x plus h minus f of x all over x plus h. I guess I can write it down. X plus h minus your initial x value, x1 value, which of course is just x. And then in the bottom, you get your h, of course, and then you realize, oh yeah, I get my difference quotient. Except now it's not f of 2 plus h or f of a plus h, it's f of x plus h, and then minus your original function all over h. So it's more abstract, but we're attempting to derive a new expression from our original function that I guess as of right now can calculate our secant slope anywhere, but of course our eye on the prize here is always our tangent slope, the slope of our curve at a specific x value. So before we introduce limits here, and of course our new f prime notation is trying to keep things as familiar as possible, so let's just make sure we know what our second y value is. We know our first y value is just our function, so really the only annoying work to do here using first principles is to get an expression for our second y value, this f of x plus h. So what is f of x plus h? Well, you're going to get a new expression once you input x plus h into your quadratic function. This one, obviously, in particular. So square your input, subtract your input, and don't forget to subtract 6. So you've seen something similar to this before, of course, where except instead of an x in the last video we had an a, and the videos before that we actually had a specific x value in mind. So this is just a little bit more abstract, but it's still the same process. So we still square a binomial here. We get x squared plus 2 times, we have 2 hx's, right? When you expand that out, you square a binomial, x plus h times x plus h. Then we have an h squared. And then we distribute this negative, or subtraction, I should say. We subtract both the x and the h, and then we have a minus 6. And there's really nothing we can simplify there. So now we go back and we set up our secant slope one last time, and then we can eventually move on to our tangent slope. So now I can say f of x plus h is this expression. It's a doozy. It's a lot of terms, but if you're organized and take your time, it's not too serious. I better leave some space because we're far from done there, because that's just y2. Go all the way over to here. And then on the bottom of my difference quotient, I always have the difference in my two x values. And keep in mind, we have to subtract our original function. If you can remember it, I guess it's kind of sitting there in front of us, but let's go up and look at the actual problem again. F of x is what? X squared minus x minus 6. So x squared minus x minus 6. So remember, what we want to see is we want to see everything without an h in it disappear. Right? So once we do that subtraction, of course, this looks a lot more algebraic than the past examples, but actually not too much worse than the last one where we looked at that point of tangency of a and f of a. So really, we have to redo a lot of rewriting here until you get the hang of this. You can probably skip a few steps. So make sure we change the signs on everything, subtract that entire function. So I'll leave that in white to say that's going to be minus x squared now. It's a little wobbly. Minus x squared plus x, once we subtract negative x, and then plus 6. And then in the bottom, we still have our h. So remember, we haven't done any calculus yet, really. We just set up a secant, or setting up our secant slope expression here. So calculus doesn't officially enter the problem here until we pull out our limits. So what I want to see is everything without an h in it go away. So I see a minus x squared, and I see an x squared right at the beginning. I see a minus x and a plus x. I see a minus 6 and a plus 6. So lo and behold, we got rid of a lot of stuff, and we now have our secant slope, which is a little less intimidating. Our secant slope is going to be, maybe we'll just go in descending order of powers again, h squared plus 2hx minus h. And that, of course, is all over h. Maybe we'll stick with a straight line there again. All over h. So now, time for some calculus. We now apply the limit. It's our slope of our secant. And I haven't really used any of our new notation yet. So, of course, just to remind you that once we have that, I'll just switch to a different color here. I can now say the slope of our tangent, and I think I'll try to keep things familiar here for one more step. And then we'll switch to our new derivative notation. So the slope of our secant line, slope of our tangent line is the slope of our secant line as h goes to 0. That's nothing new. It's just that we now have a couple of variables there now in our secant expression that we haven't seen too much of. But anyway, our secant expression rise over run is h squared plus 2hx minus h all over h. And if we try to let h go to 0, notice every single term has an h in it. Yes, we get indeterminate form, so that problem hasn't gone away yet. Okay, so before we finish this off, let's get used to our new notation, and I'll just use a different color here to say, instead of going through this whole ritual, right, of establishing our two different points and setting up our secant slope, and I mean, we can't avoid this algebra. and setting up our secant slope, but we don't need to be writing slope of secant, slope of secant, slope of secant anymore, unless of course it's helping you. And then switching to a slope of a tangent and introducing your limit, what we could have done is gone immediately to our new notation, which is to say I'm finding my derivative f prime of x, and that prime should be a little more slanted so it doesn't look like a 1, but of course I usually get sloppy with that, but maybe not in the first time we see it at least. So f prime of x is going to be this limit. So that's all that changes. So when you use that f prime of x notation, it's saying you're finding an expression that will help you find your slope of your tangent. And sometimes that gets lost on people, which is why we're doing this in 2 different colors right underneath one another here, so that you can see that it's just a new form of notation that we'll be using in, I guess, all subsequent videos from here on out. But it hasn't changed anything. Our problem still is we got indeterminate form until we deal with that 0 over 0 in our tangent. I guess we can still call it our secant slope expression there. But what we could call it is our difference quotient. The stuff in green, we could call it that as well. So if I factor an h out, or divide that h from the bottom into everything on the top, that's another way of doing it. We have h squared over h, which is h. We have 2hx over h, which is just 2x. And then finally I have minus h over h, which is 1. Now the coast is clear. We can go back to our pink and now let h go to 0. So as h goes to 0, the h in that expression goes to 0. 2x, of course, is going to stay and it's going to be unaffected. It doesn't care what h is doing because there's no h's attached to that second and third term here. And of course, we also have a subtract 1. So this thing is our derivative. So we'll say f prime of x is this expression, 2 times x minus 1. So we've differentiated our function. We have our tangent slope finder, which we now call the derivative. So keep in mind it's a little bit nicer notation, because just as one example here, maybe try to keep some of that on the screen. If we just look at a specific example, what if I want my tangent slope at, let's say, x equals, maybe we'll just write it down. So if we want the tangent slope at x equals 3, that's what you want to find. Well, that's no big deal. Now you go to your derivative, and we could say f prime of 3. So I'm going to evaluate my derivative at 3, which means I'm going to substitute 3 into my derivative, which is, of course, going to give me a number, 6 minus 1, which is 5. So evaluating your derivative gives you, of course, the tangent slope, and that's what the derivative does. So nothing new in terms of process, just getting used to this f prime of x notation. And then notice when you have that written as f prime of x, you're recognizing that your derivative that you obtained and derived from your original function is also a function. So you can evaluate that function, but please be aware that when you evaluate your original function, you get y values, ordered pairs on your function, but when you evaluate your derivative, of course, you are getting tangent slope. And I don't have to stop at x equals 3. I could put whatever I want in here as an x value, and I can get my tangent slope. So there's our introduction to the derivative via first principles. We are far from done, so if you still have I guess some anxiety over that first attempt finding a derivative or differentiating our function, we'll look at that in a few more examples in future videos with other polynomial functions. Okay, one last thing here. Forgive the length of this video, but this is our first look at the derivative, which is a pretty intense topic in calculus. So just look at some of your TI Inspire features again. So once we go under documents here, we're going to open our graph, and we're going to graph the quadratic that we just differentiated, which was x squared minus x minus 6, and there it is. Now, if you want your slope of your curve at a specific x value, that's actually in a sub-menu here, Analyze Graph. You can find your x-intercepts, your max and mins, intersections with other curves, and look at that. Number 5 is our Leibniz notation. So that's saying, oh, you want the value of your derivative at a specific x value, so we'll hit enter, which I guess is yes, and it seems to be queuing us for a position. So x equals 3 was the one we looked at moments ago. So if I type that in, we can see that it's putting 5 up by that point. Point of tangency, it's saying the tangent slope happens to be 5. That's kind of too close to the x-axis though, that 5. As you can see there, we actually, our point of tangency happens to be an x-intercept. So you can do that if you want, just a quick way of maybe getting a tangent slope if that's all you're interested in. I'll do that at one more value. How about, I don't know, -2? That's another x-intercept, and we can see there seems to be some symmetry in our tangent slopes there. They're opposites of each other. Okay, so I'm not sure if that's better than the tangent built-in feature or function in the Inspire that I showed you in a previous video. So maybe just to compare those, if you go under your geometry menu, remember you will only see this if you're in a document and not the scratch pad. If we select points and lines, tangent, but I just realized too, this doesn't really work that great if you don't have a point of tangency first. I mean, it's going to give you a tangent slope, but when I'm playing around with this, I don't know where I can actually drag it. I don't seem to really understand where my x value is unless it happens to be a 0. So I'm going to undo that, and I'm going to put a point of tangency on that curve first, which I think works better, and then we'll attach that tangent line. So I think trace is probably the easiest way of doing that. And I can say, hey, how about x equals 1, and hit enter. Type in 1, hit enter, and don't forget to hit enter the second time to actually paste that ordered pair right on your function. And now, if I maybe slide this up some, we can attach our tangent line to that point of tangency, and I can move it around and I can see my tangent equation, but I think most importantly I can also see my point of tangency. So under your geometry menu again, number 1 and number 7, and I'm just clicking on that point, and yeah, that works a lot better, at least my estimation. And now I can move that around and I can see my point of tangency and I can see my tangent slope. And if I want to change my mind and say, hey, what's going on at x equals 2? Yeah, that's maybe the best way I think of dealing with our tangent slope on your TI Inspire. But I just wanted to show you that Leibniz notation so you can actually recognize it as your derivative. But of course, all these features are very much related to your derivative because recall that is your tangent slope finder.